So, let me just kind of quiz you guys on a couple things and see if you know what to do. We're told to revolve this around the y-axis. So the fact that we're revolving this region around the y-axis sets a couple things into motion. One really important one, a representative element has to have what relationship with the axis of rotation? Perpendicular. That's right. So it is a horizontal representative rectangle. I would agree with that. And that means it is how thick. And that, of course, determines the whole rest of your setup. It has to be in terms of y. But guys, here's something I want you to think about as you try to visualize this, as you visualize the resulting solid. Would you agree with me that there is like a concavity in the middle of it? Like it's solid and everything, but wouldn't there be, like, wouldn't this void right here, wouldn't that create like a void in the solid? Like there'd be empty space in there, wouldn't there? Not a full-on hole, because right here the resulting solid would be 1 point thick, right? Like in other words, this solid would hold water, but it would only be 1 point thick. The fact that it would hold water means that there is a void. It would be sort of a bowl-like thing, yeah. That tells me that I've got to use the washer method. If there's going to be a hole or some kind of a void in there, you have to use washers. And here's what I do. I got to be honest with you. The reason why I do what I do is I don't want to mess up some mundane detail or really blow it up. And I've seen people really blow these up and get no credit at all for stuff that they should know better. And so here's what I would advise you to do. As soon as you say to yourself, oh, it's the washer method, please, for goodness sake, do this. Volume equals pi integral big parentheses squared minus little parentheses squared. There is no option. You have to do it this way. If you're going to use the washer method, it's got to be 2 separate radii squared. I've seen too many people try to do it with just 1. If it's a washer method, it must be 2. So take a quick look at what you've written down. Just look at the basic structure here. Do you have pi integral of something squared minus something squared? If you do, at the very least, you got the right structure. So that's good. Okay, so then the next piece of information we want to recognize is that we have a dy thick representative element. And so I'm going to put times dy here at the end. And that, of course, tells me that everything else is going to be in terms of y. The next easiest thing, I think, would be the limits of integration. When I've got one of these horizontal representative rectangles, do I accumulate from left to right across the region? Do I accumulate from bottom to top across the region? Which one? Bottom to top, that's right. So we're going to accumulate from here up to here. So we're going to start at y equals 0, right? How would we find the number for y where we would stop accumulating? It's the intersection point. And where do they intersect? When y is 1? Yeah, 1, 1. That's right. So integral from 0 to 1. So we'll accumulate these washers from 0 to 1. And then the hardest part about these is the 2 radii. This first radius, if you remember, is the bigger radius. Or you could also think of it as this lovely orange distance from the axis of rotation out there to the outer edge of the region. So I kind of enjoy doing it this way. I'm going to look at this and I can ask myself, literally, like if you wanted to be super duper literal, like a little kid would be, although a little kid wouldn't know the details about this, if you measure from the y-axis out to the right, what do we call that? It's called x, isn't it? If you start on the y-axis and you count over to the right a certain amount, that's literally the definition of an x distance. So you might put an x right there, right? That's literally how far it is from the axis of rotation out to the outer edge of the region. But you'd probably quickly be like, whoa, hold on. Doesn't it have to be a y? Doesn't it have to be something in terms of y? So that's where we're going to go back and say, well, that's my parabola, isn't it?
Yes.
So I'm going to say my parabola is y equals x squared. I got to replace the x with something in terms of y. What would I need to do? And so it's technically plus or minus root y is equal to x. Would I use the plus or the minus?
Plus.
Why?
Because we're doing 0 to 1.
We're doing, well, it's actually more about we're doing the right side of the parabola, right?
Yes.
doing the right side. So we will use the plus. So what I'm going to do is erase my x, and I will put positive root y. Okay, so that's my big radius. My small radius is in purple. It goes from here to here. And couldn't somebody use the same kind of process? They would say, well, from the y-axis out to the right, that's literally an x distance. So they could put an x right there. We can't leave it that way. That other function was y equals root x. What am I doing? Sorry, I've drawn the way too long of a line. It's this. Sorry. It's from here. I got myself scrunched up and I should have drawn that. It's literally an x. So it's y equals root x. You've got to square both sides. So y squared equals x. And so instead of an x right there, we put what x equals. It's y squared. Questions on setup? Like why is where things are, why are they where they are? Yeah, go ahead.
X is always top minus bottom, and looking around y is right minus left. Does that sound right?
When you say right,
Like the right equation in this case is.
well, as long as we're in the first quadrant. If
Okay,
our
yeah.
region was in
So
the
far,
second quadrant, it would be
far
left
one
minus
close
right.
one.
Far minus close, I think is better. Far
Okay.
squared minus close squared.
Correct.
I think it's a good way to think about it. Sometimes determining how much exactly is far, like that's the challenge, right? But that's the right concept for sure. Dylan,
Yeah, this is kind of a general question about integrals. Can you put a dy in front of like your expression, or does it have to be at the end?
in front of your expression. So like right here.
Yeah, can you put the dy right there?
Sure.
Okay.
I think that there's a potential for some awkward notation. If I was going to do that, I would want to make it really clear what I'm doing. So I would probably do this. Integral from 0 to 1 of parentheses dy, and then it would have to be big parentheses, and then root y squared minus y squared squared. The reason why I say that is it's not the greatest math in the world, not the greatest notation in the world, but I would say that typically what's typically accepted is that the integral and the dy are considered a grouping symbol, sort of.
Okay.
And so that anything in between the tall skinny s and the dy is considered to be the integrand.
All right.
So that's why they typically write it the way that it's written, like that.
Okay.
But there's nothing numerically at all wrong with what you suggested. Just be careful with your parentheses so that people that aren't used to seeing it that way would be like, oh, that's what he means.
All right.
It's okay. Yeah, you bet. Anybody else? Okay, so then C is a little more of a challenge. C is unlike A and B because in A, the axis of rotation was the x-axis, and B, the axis of rotation was the y-axis. This one says, what if your axis of rotation was some line x equals 3? So some non-x or y-axis line. So I want to give you a chance to try to figure that one out. We'll check your answers in a couple of minutes. Again, I think this picture will really help. So again, off to the side, it's just...
Bakers, you going to the game?
Okay, so guys, please check this out. So there's going to be a lot of elements that are the same about what we just did. There's going to be some very important differences as well. So I'm rotating around a vertical line, x equals 3. This is kind of like the y-axis, right? It's just been moved. And so this is sometimes called a displaced axis of rotation. It just means the axis got moved off of either the x-axis or the y-axis. So this is x equals 3 over here. So here is kind of your first big step. You want to look at this and you want to visualize, you want to try to think. Like we don't have time to do it here at this point. Obviously, I think you understand. Like in AB, we get out Play-Doh and we like try to visualize what this would look like with Play-Doh. But here's the big thing. Here's the big takeaway. If I did this actual rotation and created this solid, would there be a hole? Yes or no?
Yes.
There would be a pretty large hole right in the middle, wouldn't there? So, because there's going to be a hole or a void, you have to use washers. So I'm going to write volume equals pi integral big parentheses squared minus little parentheses squared. Okay? I think this is an important thing for you to realize. You want to give yourself this structure. I've seen people that know better that don't give themselves the structure that really make a mess of these. So please be careful. Okay, the next thing we got to decide, is this going to be dy or is this going to be dx? What do you think? It's going to be dy because our representative element has to have what relationship to the axis of rotation? Perpendicular. There we go. So perpendicular relationship, that makes this dy thick, meaning that I'm going to be multiplying by dy. The only thing left here are my limits and my radii. So where am I going to start accumulating these washers? For what y value? Aren't I going to start accumulating down here and stop up here? So for what y value do I start accumulating? And where do I stop? So that's actually the same as letter B, right? 0 and 1. And the radii are where this one gets tricky. So here is a radius. Here's the big radius. It's the distance from the axis of rotation to the further away function. And this is what weirds people out. We're not going to draw from the x-axis or from the y-axis. You got to draw from the axis of rotation. And Jasmine, what you said a second ago is right. It's going to be 3 minus the purple function. Can we talk a little bit about why? So, how far is it from the blue dot to the blue dot? How far is that? That's x far, isn't it? Okay, so if that's x far, and I know that that vertical line is at 3, how long is the green line segment?
X plus 3 minus
3 minus x. Hey guys, are you with me? There's just a lot of chit-chat, and maybe it's worthwhile, maybe it's not. I can't really interpret it. But for folks that are struggling, or maybe they never saw it this way, I think this is a great way to see it. I've pointed out that the blue line segment is x long, and isn't the distance from here out to the axis of rotation, isn't that 3? So if that whole thing is 3, how long is the green line segment?
3 minus X.
The whole thing minus x, right? Yeah, 3 minus x. So I could come up here and I could put 3 minus x, but hopefully I would very quickly realize that that's not an acceptable form because it's got to be in terms of y. Well, for that purple function, what does x equal? I think it's y squared, isn't it? So I think the purple function right there is y equals root x. So if y equals root x, x equals y squared. So I would replace that x with what x equals, and that's y squared. Is it making sense? Colin, question?
You can also do y squared minus 3, right? It's just in the square.
You can. Yep. Okay, and then the other one, the smaller radius. Again, I'll just remind you that from blue dot to blue dot, that's a distance of x, right? That's not what I want, though. I want to know this red distance from here to here. So once again, if we're looking for the red distance, that's the smaller radius. If the whole distance is 3, and I want the red, wouldn't I just go 3, take away the x? That would leave me with the red. That's what I want. So I'm going to put over here 3 minus x again. But wait a minute, I can't do that because I need to have this in terms of y. So for the red function is y equals x squared. What does x equal? Root y. So I'll replace that x with a root y. And this is where Josh was saying, hey, could we use the calculator? It was an excellent suggestion. Anyways, my main focus here is, does the setup make sense? Any questions on that? Now, whether you want to use Math 9 here or try to FOIL this out, all of which are doable, I would leave that up to you. Did anybody take this all the way through? Josh did. What'd you get?
17 pi over 10.
17 pi over 10. So that's roughly 5, right? 5 point something. Did you get that too, Jaden?
It's the same thing.
Did you get a decimal?
Yeah.
What'd you get for a decimal?
It's 5.341. And it's the same thing as 17 pi.
Yeah. So it's very doable without a calculator. You can ask Josh. Probably just takes a little more time and space, right? Math 9 would work there too. Okay. Questions, concerns? Okay. So a few hiccups on C. Let's see how this goes with D. Ready, set, go. This will be your last chance to do washers today. D. That's great. So, again, a couple of really common elements here that I want to make sure you guys get. The graphs are the same, so I've got y equals x squared, and I've got y equals root x, like so. But this time our axis of rotation is down below. Thank you.
Because he's a stand-up guy.
Appreciate it. Axis of rotation is down here. So once again, hopefully one of the things that jumps right out at you is that if you did rotate this and create a solid, would there not be a hole in the middle? And if there's a hole in the middle, you have to use washers. It's the third time I've said that. It's making sense? Sinking in? Okay. Cool. So then I'm going to set it up. I've determined it's washers. So I'm going to get my structure for washers set. Volume equals pi integral, big parentheses squared, minus little parentheses squared. Guys, can I be so bold as to say, in my humble opinion, if you're not doing it this way, you're setting yourself up for failure and you're being foolish. You set it up like this. You got to fill in the details still, but I think you should just commit. Okay, it's washers. It's got to look like this. I've seen people that know better that make silly, crazy mistakes that end up getting them nothing, no credit at all. Set it up this way. Okay, so hey Jasmine, what's the relationship between the representational element and the axis of rotation? Perpendicular, yes. So here's my representative element. Right here, it's perpendicular to the axis of rotation. Most importantly, making this a dy or a dx thick element. Dx. So I'll put that here at the end. I'm going to multiply by dx. Okay. It's been a couple since we've done this. In fact, since the video. When you've got a vertical axis of rotation, we accumulate not from bottom to top, but
Side to side.
left to right, side to side. So I'm going to be accumulating from the left side, which is here, to the right side, which is there, from where to where numerically?
0 to 1.
0 to 1 on the x. So there's a couple of things, a couple of trends you might see here that would be false leads. Somebody could easily look at the examples we've done in class today and say, oh, cool, the limits of integration are always 0 to 1 when you find volume. False, right? That's just false. It's going to be whatever to whatever. It just so happens we're using the same region in a number of ways. I kind of like this because even though we move the axis around, those limits of integration stay the same. That's a good illustration there. But somebody could be misled in thinking that they're always 0 to 1. Not the case. Could be whatever they're going to be. Okay, so then my axis of rotation is down here at -4. And this is where you can take a couple of different approaches. You could take this approach right here and say that this blue distance, which is from here to there, would you guys agree with me that that's my bigger radius?
Yeah.
So let me put it to you like this. Guys, I think there's so much you can pull out of this, so pay attention. Some stuff you might not be aware of. Maybe you are. Let's find out. Couldn't you literally, like if you wanted to be super literal about this, couldn't you say the distance from here to here is 4.
Mhm.
And the distance from here to here is y. That makes sense? So then you could say, well, my bigger radius is 4 plus y. Then, of course, you'd have to replace the y with something that's in terms of x. For that blue function, what does y equal?
Root x.
It's root x. So that would go here. And then what you could do is you could be super literal about this and go, well, once again, I want this red distance. So from here to here is 4. And this little itty bitty distance right there is y. So you could say, well, that's 4 plus y. But then hopefully you'd very quickly realize, I can't leave it like that. What does y equal for the red function? X squared. So I'd do this, and this would be a great setup. There is an alternative setup that maybe some of you used, and I think this is also just as good. Volume equals pi integral from 0 to 1, big parentheses squared minus little parentheses squared dx. But in your radii, you might have had this. And this is just as correct, isn't it? This is just as good. And I would say that this is actually kind of a nice way to do it. I would say I'm thinking of like Jeff, thinking of Jaden for sure, and maybe, I don't know, the folks I didn't have for AB, I don't know if you heard it this way, but one of the ways you can set up your radii, like it's very dependable. What you can do is you can go axis of rotation minus the appropriate expression, right? You can go axis of rotation minus the appropriate expression. I feel like this up here is like a very good technique, and I feel like this hopefully would be a good technique, because if that whole axis of rotation minus appropriate expression works, that'd be great. How are those the same? Why are those the same? You can factor out a negative, which would be immediately squared, wouldn't it? The fact that we're squaring what's inside those parentheses basically is saying, you know what? Whether you get 4 plus 2, you get 6, right? 6 squared is 36. What about negative 4 minus 2? It's the same thing, right? So the fact that you are squaring means that the ordering within the parentheses, within the radii, I should say, doesn't really matter. Okay? Colin, your question.
So for the, what is that called, from 0 to 1?
Yep.
Limits of integration.
Yep.
So for this, the intersection point was 1, 1,
Yep.
right? And so, but let's say it was 1, 2.
Yep.
So if you do it around the horizontal axis, you would do it from 0 to 1. But then when you do it around the y-axis, 0 to 2.
Correct.
So you go up and down, and then, so it just, whatever you rotate it around,
We won't.
you do it around the limits of integration follow. Okay, I think I got it.
Yeah, we'll just do verticals and horizontals.
But no, I just mean like, in terms of from 0 to 1.
Oh,
or from
you're
0 to 2.
yeah. So, no, I agree. Yeah,
In which
like
axis?
the originally the way you said that was right on the money.
Okay.
Yep.
So you're gonna
Just keep in mind the whole bottom to top, or left and right, and then keep track of whatever that point is. If it's 1, 2, or 2, 7, or whatever, am I going to use the 2 or the 7? Because am I going from bottom to top or left to right?
Okay.
Yeah. Yeah. Okay. What else? Any other questions on these? Okay. Let me set up Monday for us. Depends. I wouldn't ask you to do too many of these without a calculator, or I might just ask you to set them up like we've been doing. Yeah. Okay. So let's take a look here at the final topic here in 7.2, and that is solids of a known cross-section. I like these two. So I would like to give you guys some illustrations, and these are purposefully hand-drawn illustrations. I think on Monday I'll show you some high-tech versions of these, but I thought I would try to give you a sense of what we're doing here. Like I said, these are not caused by any kind of a rotation, but an accumulation of cross-sections. So let me give you an example, and I'll just give you a real generic one here. So are we all okay? I think I did this demo last year. Are we all okay with the idea that if this is the y-axis and this is the x-axis, maybe don't write that yet. Maybe don't write that yet. Would you guys agree with me that that's kind of a bird's eye view of the x-axis and the y-axis? And by bird's eye view, I mean this. So hopefully no tables break. But let's say that this, like the crack in the tables here is one of the axes, and this crack is the other axis. If I stand up here, this is like a bird's eye view. Like I'm standing right above it. It looks perpendicular and everything. This looks like an x-axis and a y-axis, right? Can you imagine what my view looks like? Okay, so there it is. But of course, if I get down here and I get a little bit more on the same plane, they don't look perpendicular anymore, do they? So my perspective has changed. So just like in art class, when you tried to draw perspective drawings, like you know how the railroad tracks seem to meet out in the distance or whatever? We're going to draw, for this, we're going to draw our x-axis and our y-axis a little bit differently. I am going to continue to have my x-axis just go across the page, just like it has forever. But I'm going to try to draw my y-axis in perspective. So it's going to go off into the distance. Does that make sense? Okay. They're perpendicular. I've just changed my perspective. So it's not like the y-axis went creak, you know. That's not what I'm talking about. I'm talking about the difference between, like your perspective. Like, don't you know that this joint is a lot of perpendicular angles, right? But when you get down on your level like this and you look at it, it doesn't look very perpendicular to me. It looks like they're kind of at a non-perpendicular angle. And so I'm trying to take, well, it'd be like even your piece of paper. Like if you had an x-axis and a y-axis on your piece of paper and you look straight at it, they look perpendicular. But if you take your paper and go, they don't look perpendicular anymore because of the perspective. Make sense? Anyway, we'll keep practicing this, but let me show you what this is. We're going to take some region, and that region very well could look a lot like what we were just working with. Maybe it's going to be y equals x squared combined with y equals root x. It could be something like this. You see the perspective? Right? It's laying flat on the plane. So what we're going to do with this, for these types of situations, we can create unique shapes. We are not going to rotate that around anything. What I'm going to do is I'm going to grow cross sections right out of it. So an example would perhaps be this. If my cross sections were perpendicular to the x, let me try that again. Perpendicular to the x, and maybe my cross sections would be rectangles. Do you see my attempt to make that come right out of the page? Or grow up and out of the top of the, or at least one of those 3D artists, right? Yeah. Okay, so then this, something like that. Do you see how they appear to be sprouting out of that region? There'd be another one back here. Do you see if you accumulated enough of those, you'd get a solid? It's kind of what we're doing. It depends. It kind of depends on how they're defined. If I said, hey, the cross sections are rectangles of height 5, then yeah, they'd be all the same height. But if it was the cross sections are squares, well, now the height's going to depend on the distance, and so they'd get taller or shorter, depending on where you are.
Okay.
So it just depends on how they're defined. Yeah.
So that could look like half a football, or
Or like a cake with a football-shaped base.
Yeah.
Something like that. That'd be pretty fun, right? Yeah, I agree. So guys, that's what we will explore on Monday's class is cross-sections, okay? Anyways, have a wonderful weekend. I'll see you then. Oh, I mean, have a happy Thursday night. Time for you.